This video is on the chi-square test. So today for the chi-square test, we are going to use the tidyverse package, the gmodels package. The gmodels package is where the chi-square test will be performed. The AER library package, that's where our data is. If you have it in a CSV, just import that CSV for the affairs data set. And the library fund modeling, just to do a little bit of exploratory data analysis. This line brings in the dataset affairs. This line over here creates a new dataset called affairs, but with lowercase a. I'm removing the uppercase affairs dataset from my working directory here. And here I'm going to create a table called cheater. So I start out with the dataset affairs. I then create a variable called cheater, which basically if you have more than one affair, we're going to call you one affair or more, we're going to call you a cheater. And if not, you're faithful. Comma, that means I'm going to another variable, occupation. Occupation already exists here. However, I know that it's a number, but in the data set, but I want it as a category. So I'm going to say as factor occupation. That makes it a categorical variable. Then I'm just going to remove the variable affairs within the data. Chi-square test is for comparing two categorical variables. Ideally, so we can clearly identify the dependencies if the test is significant, we would like two dichotomous variables. That's not always the case, and that's why we're going to do a test later on with occupation. So, a quick peek of our data. Okay, we use the freq function on the dataset cheater. We get our proportions of male and female, or proportions, this is the count. Here we have the frequencies of children, the proportions, and the frequencies and proportions of each occupation. Note that we already know that these two occupations, 2 and 7, have very small counts, but we'll deal with that later. Without further ado, let's begin our test. So we use the function crosstable. Note how crosstable is spelled. Capital C, capital T, R is case sensitive. This is from the package gmodels. We're using the dataset cheater, the variable cheater, dataset cheater, variable gender. We are going to test whether if there is a dependency between gender and being a cheater. And to do that, again, another comma, and we are specifying that we want the chi-square test. We run this. Again, we have a p-value. Look at the first p-value. No need to look at the second one, but if you'd like to, it doesn't matter. If our alpha is chosen to be 0.05, then we are retaining the null hypothesis, and we say that there is no dependency between cheating and gender at the alpha equal 0.05 level. Now let's check out if having children has any effect on cheating. We see our p-values. Again, this is the only one you should look at, but you can look at this one all the same. Just a stricter test. We do reject the null hypothesis here, and we say that there is a dependency between cheating and having children. Now, the gmodels produces a lot more output than just that chi-square test. Creates a very, very informative table. Okay, we have cheater in our columns, and in our rows, and children in our columns, and we have 5 statistics for each cell. Okay, so let's take a look at what those 5 statistics are. We have N, chi-square contribution, and then row proportion, column proportion, table proportion. So N, 27. There are 27 cheaters with no children. There are 123 cheaters with children, and so forth. Row total, we have 150 cheaters, which account for 25% of our data. As far as the column totals, we have 430 people with children, and that accounts to, for 71.5% of our data. We have a total of 601 observations, or 100% of our data. Then we have our row proportion, column proportion, and table proportion. Probably the most informative are going to be these two. And depending on how you set up the rows and the columns, which variable is which, one is going to be more important than the other. So I can say that 18% of cheaters have no children. 82% of cheaters have children. So you'd say, well, if you have children, then you're a cheater. Really? Well, it really depends on, but don't we know that there's a lot more people with children than without? So, of course, there's always going to be a higher proportion, or there is likely to be a higher proportion of people cheating. Again, people cheating, it's a row statistic, with children. So to do this more accurately, what we need to do is say within each category, meaning not having children and having children, what proportion are cheaters? And we're talking about a column. So in other words, a column statistic, such as this one, 15.8%. 15.8% of people without children cheat. 84% of people with no children are faithful. 28% of people with children cheat. 71% of people with children don't cheat. So now we're going to say that given that in this scenario, the column statistic is going to be more informative to be able to determine, we have a significant p-value. We know that there is a dependency between having children and not versus cheating. So we take a look at a concept called the relative risk. So for relative risk, let's go here to a nice definition for relative risk. Relative risk is a ratio of the population of an event occurring in the exposed group versus the probability of the event occurring in the non-exposed group. So, what is the probability of cheating in the exposed group, exposed to children? The probability of this occurring is 28.6%. What is the probability of cheating occurring in the non-exposed group? 15.8%. Divide those two numbers as I have here, and you get a ratio of 1.81. Therefore, I can say in the relative risk, people with children are 1.8 times more likely to cheat. Interesting statistic there. So now I have a dependency. I know that there's a dependency because of the p-value. And then I can also express how the dependency affects with or without being exposed. In other words, being exposed to children, having children. So that said, I can also give a magnitude to it of 1.81. In other words, 80% more likely to cheat if you have children. Okay. Continuing. So we have occupation. Occupation, remember, has multiple levels. Cheating has 2 levels. Note how here I have cheater versus children, but here I flipped it around, occupation versus cheater, because I want occupation in my rows. Why? Because when I run this, I want to be able to see it. In other words, if I had, instead of occupation being the rows, they were the columns, it would expand way far beyond my screen and it would be a little bit awkward to see. This way it's a little bit easier to see. Nevertheless, we even got a little warning here. and it says the p-value 0.34. We are retaining the null hypothesis, and there is no dependency between cheating and occupation. Please note that if this were significant, we would not be able to truly understand which ones exactly are the ones that you'd be more likely to cheat. Yes, in this case, because the way this is set up, I want to see the row statistics, and I can see 0.231, 0.204. Remember, this 0.231 is not too credible. I only have 13 observations. I have 0.319, seems a lot bigger. 0.3, smaller, kind of in the middle, really much bigger, but 13 observations, not too credible. And I would have lumped this between two groups. I would lump these occupations into a higher proportion and lower proportion of cheating and rerun the chi-square test as a 2x2 test. But this did come out as insignificant, and I'm just going to leave it alone. Now, continuing with this, what happens if I want to say cheating by gender and having children? Okay, I want to introduce a third variable. I want to know that if you have children, I want to know that the gender came out before as not significant. There is no dependency. But if we split it up between, do the test again of cheating and gender for those having children and those not having children. So I'm going to create two data sets. Having children, not having children. Take a look at the code. Then I'm going to run my test. So this is having children. We know that if you have children, you're more likely to cheat. Yet, the gender difference for people with children, okay? The p-value came out to 0.7. So it's either above or below your alpha. However, this is a big p-value, much bigger than when we ran just gender by itself. So it seems like men and women, when they have children, there's no difference. They both seem to, cheat. If we take a look at this, let's take a look at our column statistics, okay? So the proportion of, if we look at just females, 27.8% of females cheat. 29.4% of males cheat. So they seem to cheat all the same. These numbers seem to be quite similar enough that our chi-square test came out as not significant. No dependency. Now, if we say if you don't have children, our p-value is still above the 0.05, although much smaller. Well, let's take a look. 44% of females with no children cheat. 55.6% of males cheat when they don't have children. So you'd say, well, that's a pretty big difference. But look at our N. Our sample size for the population is 171. Remember, these are just the people without children. If this data set were bigger, more likely with the same proportions, more likely we would have a significant p-value. But for this population, we cannot conclude anything as far as dependency goes. And that's it for our chi-square test.